So slowly we'll be building the C++ structures. Wherever required, we'll use them. Okay. Okay, then let's go to today's lecture then. So yesterday we were discussing about the different sorting techniques. Okay. So can someone quickly recap me what were the different sorting ideas which we discussed yesterday? Yeah. So bubble sort, selection sort, yes. Yes, selection sort, yes. And what different kind of ideas did you think did we discuss about? So, one part of it is uh, moving the smaller element to the start continuously. The other idea is larger element moving to the end. And other one is the cards idea where you have some sorted sequence. And from the unsorted, array, you pick one element, and place it in the right position. Right position. Fourth idea is where you sort smaller parts and then use them to sort larger parts. Okay. So the smaller is named as bubble sort. Moving larger. Okay, sorry. This is selection sort. So moving smaller is a selection sort. Larger element moving to the end is a bubble sort. And this will be the insertion sort. And then this will be the merge sort. Okay. For both the selection sort and bubble sort, we have discussed the algorithm. It's highly recommended that you code them. Okay. And then insertion sort. Okay. So insertion sort. The idea is that, yes, the cards idea is always there. You have two parts, unsorted part and the sorted part. Pick element, pick and place. Pick and place at right position. Okay. Yeah. So any idea of the code? Can you think of code on how it's happening and all? Can you briefly try to write the code? Comparison. Yes, we have to compare the adjacent elements. Keep checking. So basically it's like you have an array, you have the sorted part of the array. Till assume that we are at some in midway of doing the sort. We have the element here. What will we do? We'll check with this element. This is not there. This element does not match. This element does not match. Here is the place where it has to originally go. Then basically we have to put this on here, move the all elements a step ahead. Will this algorithm work? Okay. Okay. Just to provide you a little bit of pseudocode, let's say we move from, see, a single element array is always a sorted array. Single element, always sorted. Okay. So let's say I'll start from my I to n minus 1. So basically what I'll be doing is I'll start from I n minus 1. From the index 1 to n minus 1, sequentially, I'll try to place this particular index element in its right position. Okay. Now what I'll say, let's say this is my key. My key element is ARR of I. This is the element which I want to place. Okay. What I have to do? I have to keep iterating through the sorted array. So basically from 0 to I minus 1, I have to keep checking.
मिडिल क्लास मैम भाई अभिनव
Am I audible now? Okay, great. Sorry, little net issues. Okay, till where could you hear me? Hello. Till where could everyone hear me? Ma'am, repeat. Okay. Now, from where shall I repeat? Could you not hear the entire algorithm? General. Okay, fine. Let me do that. Okay. So, okay. So, in an insertion sort, the idea is that suppose if you have a if you're playing rummy, what will you do? If you have 4 and 6, you'll bring 5, place 5 in between that one and make it a set, right? So similarly, you can perform one way of sorting the things is that way. So what we do in in case of insertion sort, you have two parts. You have one part of sorted array. You have other part which is not sorted. You take one element from an unsorted array and find its place and insert exactly there. So create a space for this element and insert it there. Suppose we have this. Okay. We have this entire array. Yeah. We have this entire array. Suppose assume that from 0 to I minus 1, it is already sorted. You want to insert the ith element into its position of the sorted array. What will you do? You keep searching, find its position such that left side element is smaller, right side element is greater than that one, and insert it here. Move all these elements by one step. Is this idea clear? Inserting it and moving the remaining elements by one position. Okay, Ashish says clear. Ashish says, what about remaining people? Is the idea clear? Okay. Okay, Sachin also says yes. What about remaining people? Why is the class little dull today? Okay, Manish says yes. Okay, Rashmi also says yes. Okay, Prabhojit says yes. Okay, great. So let's try to code up this algorithm. Let's try to code. Let's say what I'm doing. Single element is always sorted. No matter what, single element is always sorted. So we can assume that the first element is already sorted. So what we'll do is we'll move from I is equal to 1 to n minus 1. From first element to the n minus 1th element, we'll keep moving, and each element will pick and place it in the right position of the previously sorted array. Okay, let's say Now, let's take a small example and then let's do a little small dry run and then let's try to include. Okay, I have 2, I have 4, I have 5. This, let's say this part is sorted. My next element is 3. Now, this element I'll compare with 5, still greater. This element is greater, so I'll check if there is any element greater than this one. Let's say, suppose I have already stored this element. Let's say I said my key is equal to 3. What I'll say, while I'm moving in this direction, I have to create some space to insert 3. Okay, so what I'll say is remove 5 from here, store 5 here. Okay, and now let's we have checked 5. Now let's check 4. 4 is also greater. I'll check if there is, till I find a smaller element than this one, I have to keep checking. 4 is greater than this one. I'll say move 4 here. 4 I've moved here. Now I came till 2. Okay, when you're 2, done, stop. Now this place is empty. You have moved 4 and 5. Place 3 here. Place 2 here. Now your 4 elements are sorted. From 3 elements sorted array, you have moved to 4 elements sorted array. Okay, now let's write the same thing in terms of code. Let's say my key is ARR of I. Where did I start iterating? If I'm at ith index, I have to check from I minus 1 to 0. Where I have to check till I find a smaller element than this, I have to keep iterating, right? And I have one condition is that one. Other condition is if I reach the starting point. Suppose if my element is 1, then maximum I'll go to 0th index, not more than that one. So we have 2 termination conditions. While j, okay, so while writing a while loop, the first thing which I have to do is initialize j to I minus 1. While j greater than or equal to 0, and one more, what is that? Till my ARR of j is greater than key, I can iterate in this loop. I can iterate and find the position. What I'll be doing in this loop, I have to move elements also. What I'm doing, ARR of j plus 1. I've moved 5 from index 2 to index 3. ARR of j plus 1 is equal to ARR of j. I'm creating empty spaces every time. And every time I also subtract j minus 1. Then after exiting this loop, whatever the key element you have, now insert that at this position. Suppose if you keep running, at this index, you'll exit the loop, but you want 3 to be at the next index. So just do ARR of j plus 1 is equal to your key element. You complete all the indices. Is the algorithm and code clear? Okay, Ashish says yes, Rashmi says yes. What about remaining? Ma'am, repeat while loop. Okay. One more example. Okay. Can we do a dry run once? Okay. Okay, we'll do that. So let's suppose for one small example, we'll do a dry run. For this example, I'll repeat the example. I'll repeat this example again. Is that fine? Okay, cool. So suppose we are at the intermediate tree run of this one. 2, 4, and 5 are already sorted. Okay. Now the element which I have is 3. So I'm at the index 0, 1, 2, 3. Okay. This element I want to place. The idea is that now my final array should look like 2, 3, 4, 5. Okay. What happened? The 3 has come to one position and this 4, 5 are moved. Okay. Let it not be 3. Any x element. Let the element be any element. Definitely it will have its place. Whether it is at the start, any element, if you have an array, let's say 2, 4, 5. Let this element be anything. It can fit here, 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 here. Definitely out of the 1 positions, it will fit at some place. Do you agree with that one? Any element in a sorted array can find a place and make the array sorted again. Okay, this is the central idea. Okay, so what's happening is array is a contiguous sequence. So when I insert 3 at some position, I have to move the remaining elements. 0. Okay, so I have 0 and then 1 and 2. Sorry. We have 0, 1, 2, 3. Initially 4 and 5 were at 1 positions. Now 4 and 5 are at 2 and 3 positions. So I have to insert and I have to place. I can do 2 things. First, find the index. Find the index at which I have to place 3. Place 3 and move these elements. Okay. So to do this one, what we have to do? First, we have to store 3, store 5, 5, store the remaining array, move each element by element. What we are trying to do in this while loop is, when you know strictly 5 is greater, then definitely you'll have to move 5. If you know 4 is strictly greater, then you'll have to move 5. That's what we are trying to do there. Okay. So we are finding the position and moving the elements at the same time. Finding the index plus moving at the same time. Okay, now let's start. We have 2, 4, 5. 0, 1, 2, 3. I'm searching for my key is equal to 3. Okay, done. My j is equal to I minus 1. So my I is also 3. I'll start my j at 2. While j greater than or equal to 0, that condition is satisfied. ARR of j greater than key. What is my ARR of j? 5. 5 is greater than 3. Okay, this condition is also satisfied. Tick mark for this also. Then if the condition is satisfied, what I'm doing? ARR of j plus 1. What is my j? ARR of 3. I'm making it ARR of 3 is equal to ARR of 2. Okay. So, and I'm doing j is equal to j minus 1. That's another iteration. Let's see. Okay. Now the array will become 2, 4, 5, 5. It might appear that we have lost 3, but in the form of key, we have stored the element 3. So we are not removing that element now. Okay. Next array, Sachin asks one doubt. Okay, let me clear that one. If array is large, how to know which index element we have to move for sort? Okay. Here, what are we doing? For each iteration we are moving from I is equal to j is equal to I minus 1. We are iterating for every element. We are starting from the previous element and we are iterating till the start of the array and experimenting and checking at which position we have to fit the element. Okay. Is the first step clear? Is the step clear? Okay. Sachin says yes. What about remaining people? Okay. Okay. Let's iterate again. Probably you'll get a better idea. Okay. Now let's say j is equal to 1. J is, this condition is j is greater than or equal to 0. And this condition is ARR of j greater than or equal to key or not. Okay. ARR of 0 condition is that. ARR of j. What is ARR of 1 for us? Now this is our new array. 0, 1, 2, 3. What is j? 4. 4 is greater than 3. Condition is true. What I have to do? ARR of j plus 1. J is 1. ARR of 2 is equal to ARR of okay. What I'll be doing is ARR of j plus 1 is equal to ARR of j. What is j plus 1? ARR of 2 is equal to ARR of 1. So my new array will look like 2, 4, ARR of 2, I have to copy ARR of 1, and then I have 5. Okay, great. Next, j is equal to 0. This condition is satisfied. 2 greater than 3, not satisfied. So loop exited. Okay. Loop exit. After exiting the loop, what am I doing? ARR of j plus 1 is equal to k. At this condition, my loop has failed. So this is the next smallest element. I mean, the element which is just smaller than key is the 2. So if it's just smaller than, then the correct position for 3 is the immediate index after this one. The condition has just failed here. The correct position of 3 is the next index. So what I'll do? ARR of my j plus 1 is equal to the key. Key is what? Something I've stored here. What is j plus 1? ARR of 1 is equal to 3. What is my new array? 2, 3, 4, 5. Now from a 3 sorted element to, we have moved as 4 sorted element. Is it clear now? Okay, Sachin says yes. I'll wait for remaining people also to understand. Okay, Ashutosh, Ashish also say yes. Okay, great. If you are worried about, suppose, let's say, we have 2, 4, 5, and 7 itself. Okay, these 3 elements are sorted. We have the 7 here. What will happen? My j is equal to, I'll start from j is equal to 2. J greater than or equal to condition is already satisfied. My 7, my ARR of j, 5 should be greater than 7. So this condition has failed now. It will exit the loop. After exiting the loop, what am I doing? ARR of j plus 1 is equal to key. This is my key element. What is ARR of j plus 1? ARR of 3 is equal to key. Key is 7. So again, 2, 4, 7, 0, 1, 2, 3. So if the element is already in the sorted order, basically you'll not go into the while loop and exit. Maybe I think this can give you a little bit better clarity. Okay. Mani says yes, Ashish, Ashutosh, Sachin says yes. Ankit, what about you? Got it? Okay, Rashmi says also clear. Okay, Ankit also says yes. Ravi Shankar, is it clear?
Ma'am, can I say something?
Okay. Who is it speaking?
Sachin Nagar.
Okay. Yeah, go ahead.
Ma'am, take as like we take a array 2, 3, like a T 2, 4, 5, and you put the 3 back. Then you directly take a 3 and index value. Then you iterate then 3 from 4 with 4 and 5. With the algorithm, how do we know that 3 is not a proper position? Okay. That is my question.
Acha, okay. So what I have shown is one iteration of this part. Okay. I have shown one iteration of this part, but there is one more for loop outside also. Okay. What will that do is, suppose I have random array, say, let's say 2, 9, 1, 4, 7. For the first time, I'll try to insert 9 in this place. Then 2, 9 will be sorted. After 2, 9 is sorted, I'll go to 1. Now 1 is my key. This is my sorted array. I'll arrange this one. The array will change into 1, 2, 9. Okay. Then I have 4. This array is already sorted. This is my key element now. Then again, I'll repeat this process. I'll search for this correct index. Then it will become 1, 2, 4, 9. So this is after the first iteration, second iteration, third iteration, fourth iteration. And now I have this part is sorted already for me. 7th one is the key. Then again, I'll repeat our process, repeat our inner for loop. Then I'll have 1, 2, 4, 7, and 9. So this algorithmic part I was discussing for this internal for loop only. I thought the upper for loop is I'll iterate for each element. So we were discussing about one intermediate case. Okay, ma'am. Got it. Okay, great, great. Okay. So I'll give you maybe a minute or two more to just think about it for one more minute. Then we'll discuss the next algorithm. Rishabh also says yes. Ravishankar, clear. Okay, great. And it's highly recommended that you go code these things again. I'm like almost the entire code I'm writing, but for your practice, for your understanding, in insertion, sort key is also given. No. So you're given a random array. You're given any array. This particular key, you'll iterate through, you'll sequentially, you'll iterate over the array, make each element key for each other iteration, and then repeat the process. Every element will become key once. In other words, let me repeat this part again. Okay, you have 29147. Okay, single element is always sorted array. Make increasing order. Okay, single element is already sorted array. I'll start from my first element. This is, say, my first iteration. This is for the outer loop. Okay, outer loop first iteration. For outer loop first iteration, this is my key. If this is my key, we have learned how to find in the inner loop, this algorithm will run. J is equal to 2, checking conditions, finding its place. After finding the place, after first iteration, array will be 29147. Now, this is my sorted part. Okay, here I was equal to 1. Now I will become 2. So this is basically my key. Let me not fill it up here itself. Let me use another row. 4, 7. Okay, here I have 1. At iteration 1, my 9 is my key element. At iteration 2, 1 is the key element. This part is already sorted. Okay. Then what will happen? I'll find a place to insert 1. That place will be this one. I'll move the elements, put it in the right position. Now these 3 elements are sorted, 4 and 7. I'll go to my third iteration. This will become my key. Now in the previous sorted array, from I minus 1 to 0, in the while loop which we wrote, I'll iterate, find its place it at the right position. Now this is my new sorted array. I have 7. Iteration is equal to 4. This is my new key. This is already sorted. From I minus 1 to 0, I'll run a for loop. I'll find its position, place it there. So my size is 5. I is equal to n minus 1. Now my I became 5. The outer loop also will exit. Okay. Hope everything is clear for everyone now. Okay. Great. Okay. We'll move to the next part. So when I mean array in C++, consider using vectors. Okay. It will be a vector int variable name ARR. Okay, good. Then before discussing merge sort, let us discuss a subset of merge sort. Okay. Suppose I say the problem is, given two sorted arrays, turn them into make one sorted array using. Okay, suppose I say I have 2, 5, 7, 11, 14. And here I have 1, 3, 8, 10, 13. Okay. This array is individually sorted. This array is individually sorted. Okay. What you need to return sorted array combining all the elements. Return sorted array combining all the elements. Any ideas? What are the ideas? Take first element from both, compare, and then small one into the new array. First combine, and then sort. Okay, we have got good number of answers. So Sachin says, combine both of them, store into a new element, store into new index, store into a new vector, store into a new vector, and then just do a sort vector, vector dot begin. Write your comparator function, however you want it to be, whether it's in increasing order, decreasing order. Write your comparator function. Second method. Here, in this example, what we have not explored is each array is actually already sorted. Suppose if we give you two unsorted arrays also, this algorithm will work. But there is a special condition called as sorted. Can we make use of this one? And reduce complexity? Okay. Think for a minute again. Later, let's discuss. Hint is that in this entire array, there is no element smaller than 2. In this array, there is no element which is smaller than 1. Okay. If you all agree with Jatin's idea, type yes. Or if you have any other idea, type out that idea. Okay, Ashutosh says yes. Okay, let's see. Suppose I maintain 2 pointers. Okay, one for the first array, other for the second array. Okay, I have, say, suppose 2 and 1. Let me rewrite the arrays here. 2, 5, 7, 11, and 14. And then I have 1, 3, 8, 10, 13. 2, 1. There is no element smaller than 2 in this entire array. There is no element smaller than 1 in this entire array. Okay. So, in my new array, the smallest one will be either of these two. So I'll compare this one, whether 2 is small or 1 is small. If 1 is small, let's say, suppose I have created a vector int v. Okay. Then I'll do, for each one, I'll compare, and then sequentially I'll push. Vector dot push underscore back, compare and push 1. Okay. After pushing 1, I'll say this element I've already placed in the new array. So I no more require this one. I moved it to 3. Again, an algorithm is the same thing. Okay. There is no element which is smaller than 3. There is no element which is smaller than 2. Now again compare. Now push 2. Move it here. Push 3. Move this element here. Then 5 and 8. Push 5. Whenever you push an element, move it, keep moving the pointer. Okay. Then you have 7 and 8. 7 is the smallest one. Push it here. 7. And then I have 11 and 8. I'll push 8. Move it here. 10 and 11. Push 10. Move the pointer here. Then I have 11. Then I have 13. Array is done. This array is left. I pushed 14. This is also empty. I have an array. Okay. If we have used M1, what would be the time complexity? First of all, you have to copy all the elements. That will take O of n. Let's say both are of same size. For now, let's assume that both are of same size. Plus some sorting complexity. This depends on the algorithm which you are using. Okay. But here, given 2 sorted arrays, within just O of time, you could solve the things. This is the time complexity. Okay. Suppose if you use a bubble sort or something, this will become an O of n square. But here you don't have that complexity. Within O of 1 only, you're able to create an array combined of both the elements, and that is also in the sorted sequence. Everyone clear with this idea? Okay. Okay, great. Okay, Ravishankar says yes, Ashish says yes, and then Sachin, Ashutosh. Okay, good. So now Anish also says yes. Okay. So now let's see. Here we were given 2 sorted arrays. Suppose now we are given an unsorted array. Unsorted array. Required thing is sorted array. Can we make use of the above idea and design a sorting algorithm? If yes, how? Keep thinking. I'll keep giving hints. Okay. So can we break our array? and sort them individually. And let's say the above thing is called as merging of two arrays. Sort them individually, then again use merge. Okay, that's one idea. Okay, then one more thing is single element is always sorted. Okay, so shall we keep on breaking till we reach single element arrays? And how shall we break this? In binary search, we got a lot of advantage when we broke into half and half. Shall we do the same thing here also? Okay. Okay. Let's take a huge array. Yes, recursion. Yes. So what we'll do is, let's take a little bit larger example. Let's say 16, 1, 4, 8, 6. Okay, I'm almost writing a sorted array. Let's say 3, 10, 5. Okay, let's say this is our array. Okay, this is my low, this is my high. 0, 1, 2, 3, 4, 5, 6. Okay, find the mid. Yes, find mid. What is mid? Mid is equal to 3. Let's say from 0 to mid is one array. Now break it into two parts. 16, 1, 4, 8 is one array. 3, 10, 5 is one array. Okay. Here, what is the mid element? Let's have the indices, the ASCIIs. 0, 1, 2, 3 are the indices. 4, 5, 6 are the indices. So this array, we have broken it into two parts. Okay. Now, let's break this one also. If we break, what are the elements? So it will become 16, 1, 4, 8. Here 4 plus 6, 10 by 2, 5. So let's say we are including mid in the previous array. Let's suppose in the previous thing we include the mid. So we have 4, 5, 6. Sorry, I wrote the indices, which is wrong. So I have 3, 10, and then I have 5. Okay. Then 2 element array. So it will break into 16 and 1. And then I have one more element also, 2 elements. They'll break into 4 and 8. Okay, this is my single element. This is single element. This is also single element, single element. Here I have 2 elements. Okay, here I have 1 element. Here there are 3 elements. Here there are 4 elements. 2 elements. Let me break again. I have 3 and 10. 5. Let 5 stay as it is. Now, I have 2 single elements. Okay. Let's say I use this black box operation called as merge, this merge operation, and combine these 2 elements. Then can I change my, and I change my new array to 1, 16. Okay, so basically it's okay. I use a temporary array here, store them in the sorted sequence, and copy back to this array. Okay, that's fine. I did 14 and 16. Now 4 and 8, they're already sorted, it will remain in the same sequence. 3 and 10 already sorted, fine. Single element is already sorted. Now the step is over. We have come down till the bottom. We have bottom till all the single elements are there. Now we are traversing back. Okay. Now, if you have to create a merge array, how the merge array will look like? It look like 1, 4, 8, and 16. I use 2 pointers. Compare, go back. I have 1, 4, 8. Then here I'll have 3, 5, 10. I'll have 3, 5, and 10. Now I have 2 different sorted arrays. I'll use this above step to combine. It will become 1, 3, 4, 5, 8, 16. Okay. Did everyone get the idea? Okay. Okay. Prabhajit says yes. Ashish also says yes. Rashmit says yes. Rahul says yes. At last, how they sort. See, you have traveled down for once. You came back and see your array is sorted. You kept on using your merge operation for smaller parts, and you have created a sorted array for the larger part. Just using the fact that single element is already sorted. So you kept on building and adding the elements. Sachin, did you understand, or should I repeat it once again? Okay. So I have reached, let's say, this is my step 1, step 2, step 3, and step 4. Okay. Here I have this element. From my previous step, I got this array, I got this array. In the previous question, we applied one operation, right? We applied one merge operation. This sorted array, this sorted array. On these 2 sorted arrays, we applied a merge operation and got a single array. Same thing I was trying to do here. I got 1, 4, 8, 16, and I got 3, 5, 10. Okay. Now what I do is I have a pointer here, I have a pointer here. I write 1, move my pointer, write 3, move my pointer, write 4, move my pointer, now write 5, move my pointer, write 8, move my pointer, 10, the array is finished, 16, the array is finished. Okay. Sachin, is it clear now? Okay. An array I divide into subarray, subarrays to subarray, subarrays to subarrays, till single element. Keep merging to get the final array. Okay, let's try to write a code. Can I use a recursive code? Because the same thing I'm doing the same thing again and again. Smaller array, I'm sorting it. I'm using that to sort a bigger array. Okay, let's say I have, let's say void merge sort. I received a vector int. Let me pass the address of the array. Let me pass the array by reference, because I want to make changes in this array itself. Okay. Can you explain after breaking? Okay. Give me one. Okay. Okay. Let's not go to the algorithm before everyone understands. So while breaking, what I did is I have basically how we break in a binary search, low plus mid by 2. Low plus mid by 2. The same thing I did here. I have index 0, I have index 6. I did 0 plus 6 by 2, that is equal to 3. So 0 to 3, I kept it in 1. I kept it as left part. Let's say this is called as left part and this is called as right part. From mid plus 1 to end, I kept it in the other part. Okay, then I have 0, 1, 2, 3. I did 0 plus 3 by 2, that's 1. So 16, 1 and 16 and 1 go here, 2 element array here, other 2 element array here. Okay, got it, cool. So next we have, let's say I said void merge sort, and I say vector int @arr. I'm using @arr, which means I'm sending the address of the array and not a copy of it. So if I make changes, those changes have to be reflected, because if you see from this step, there are some changes. You want these changes to be reflected. Then only the smaller part will become sorted, and you can combine these sorted parts. So whatever the changes your lower steps are doing, you want that changes to be reflected for the higher steps. Then you have to pass the address so that the local functions, the individual functions which we call, make changes at the same addresses on the same array. If you remember, while doing recursion, we did not pass the elements by reference. We passed it by value. So locally they had different values. If you remember, x plus 1, x in one function, x had one value. Another call of the function, it had another value. But while doing a merge sort, we are performing the operations on the same array. We want changes to be reflected in that array. Only when changes are reflected, you can move to higher steps. Okay, did you get that idea? Why am I passing it by reference and not by value? Everyone? Yes, okay. So I said vector int, pass it with the address, and pass a low value as well as a high value. Okay. Then apply this algorithm. Let's say I find a mid value. That mid is equal to low plus high by 2. Apply merge sort on for the same array. Low to mid. Apply the same algorithm again. Then do a merge sort on ARR of mid plus 1 to high. So sort this one. Apply the algorithm. Now merge sort basically returns a sorted array from low to mid. Okay, this merge sort of this vector means that this particular function will return a sorted array from indices low to high. Okay, both included. This merge sort of ARR low to mid means that it will return a sorted array from low to mid. This merge sort will return a sorted array from mid plus 1 to high. Now use merge, pass both ARR, pass low value, pass mid value. Let's as of now use this as a black box. The algorithm in the black box is the algorithm which we previously discussed, this part. Okay. Use this as a black box, send both ARR value, low value, mid value, high value, so that it will be able to separate those two elements. Okay, merge and give me the answer. Is my recursion function right? Are you able to understand or not? What is happening? Okay. So is my recursion function correct? Or are there any mistakes? So what are the two important points to write a recursive function? Ma'am, in last, we have to join two sorted arrays. Yes. All those things, as of now, consider it as a black box. We'll write the merge function also. But this merge function, as of now, consider it as a black box. Once you understand this part, we'll write the merge function. Ravi Shankar, is that clear? Okay, good. Yes, Ashutosh rightly pointed out, I did not write a termination condition. Okay, if I don't write a termination condition, then it will run infinitely. So what is my termination condition? Anyone? What should probably be the termination condition? Yeah, high greater than low. Yeah. Any other answers? Array size, maybe? Yes. I've faced a problem when I was giving exam. You mean the exam on 26th? Let's discuss those things later. Let's complete this part. Yes, I think Ravi Shankar, Ashutosh, both are right. Array size or low greater than high. Basically, high minus low or low minus high indirectly will give us the array size. When do we stop? When the array size is 1. Okay. When the array size is 1, we say that it's already sorted. So let me write a condition like if begin greater than or equal to end, return. So if begin and end are equal, it is a single array. The array size is 1. It is already sorted. I no need to perform any other operation. Or during this process of mid plus 1, mid minus 1, if they have crossed each other, if the start pointer and end pointer or the low pointer and high pointer have crossed each other, it means that those array size has even become a negative, not even 0. Then those arrays I need not sort. So is the termination condition clear? It was submitted, but I have solved all. Okay, Ankit. Let's look into it. So did everyone understand this part of the code? I'll wait for 2 or how much ever time it might take. Understand this part, then we'll write the merge condition. Okay, Ravi Shankar says yes. Jatin says yes. Okay. Can you see my test paper? I'll speak with the team and check. Okay, what about the remaining people? Did you understand? Ankit, what about you? Did you understand the merge sort code? So Pranav says yes, Ashish says yes. What about Manish? Anish? I did not see Lahari's message today. And what about Jagadish? I did not see his message also today. Rashmi, what about you? Rashmi says clear. Anish also says clear. Manish says done. Okay. Yeah, sure, Ankit. I'll speak with the team and check the paper. Okay. So hopefully everyone are in the same. Everyone understood this part. Let me write the merge function. Okay. Let's say merge. Let me say void. After the merge function, in the given array, in the given space only, I'll return you an array such that for my given limits, I'll solve you the problem and give. Okay. Let's say void merge vector int @arr. In the same array only, I want to make changes. In the same array only, I want to correct everything. Okay. I received int low, int mid, and int high. Okay. Now what I'll do is create my left and right arrays. Okay. Let's say vector int L, vector int R. Okay. And observe, before I perform the merge operation, my arrays from low to mid and mid to high, individually they are sorted. Keep that condition in mind. Okay, now I'll do for I is equal to low to mid. Okay. L dot pushback. Okay, sorry, give me a second. My pencil is out of charge. Okay, keep thinking on how will I write the algorithm and put the elements of the sorted sequence back into the original array. Okay, so from I to low, I copy and push the elements into this vector, and I'll say push ARR of I. Okay, then from I is equal to mid plus 1 to high, push these elements. So from the original array, suppose this merge function was called at this stage when my low is 6, when my low is 4, 6 on this part. So recursive call will happen for this one. Recursive calls will happen for this one also. But this one also, sometimes it might call merge on these two functions after the smaller parts are sorted. Okay. So I've copied both those two elements. Now, let me declare the pointers. My I is the left pointer, I initialize to 0. J is the right pointer, I initialize that also to 0. And what I'll do is, initially in the previous algorithm, what we thought, we already have one sorted array. We have one sorted array. We'll create a new array. And from there we'll index. From there we'll insert. Now what shall we do is, we created duplicates of the original array. Okay, 2 elements from low to mid and mid plus 1 to high. Let's say we go and insert these elements into the original array. We start from low, from its lowest position. So from low to high, we have to replace the elements. We start from low and keep inserting elements. And as we have already passed the address, no need to return anything. Make the modifications in the original array itself. Okay. So I'll say the pointer to the array which we want to make the changes and keep the array, sorted array there, let be K. That will be the K pointer. This is left array pointer. This is right array pointer. This is the original pointer. Okay. Now let's loop. While I less than L dot size, okay, and J less than R dot size. Okay, basically I made use of the vector inbuilt function. So I can iterate till their sizes are ending. Okay, more than that, I cannot compare and iterate. So both have to be within the size. Only then I can compare that elements. Right. What will I do here? Those are the termination conditions. Let's say if my L of I is greater than R of J. What shall I do? What element should I place at AR of K? My L of I is greater. Default assume that we want to sort the elements in the ascending order sequence. If my L of I is greater than R of J, which element has to be placed at ARR of K? Ashutosh says R of J. Ravishankar also says R. Rashmit Kaur also says J. Okay. So as this is an ascending order, the R of J is the lesser element. So we say ARR of K is equal to J and move the J index. Keep the I index as it is. Okay. Else what do we do? Put the right side element and move the right pointer. Now it will enter into either of the case. One element will get placed in the original array in its right position. Now move the original index also to the next one. Okay, done. It seems that we are done with the things here itself, but imagine a case where you have your left array, you have your right array. Your right array elements are all inserted, but your left array elements, these small part are left. I mean, this loop exited because of this condition, the loop got exited. The loop will keep on executing when both the pointers are within the size limit. What will happen if two elements are equal? If two elements are equal, it will get into the else condition. I++ will happen. Accordingly, again, you can iterate for the remaining things. Say suppose you have 3, 4, 3, 5. What I'm saying, my pointer is here, my pointer is here. I'm saying first of all insert this value, move this one. Now compare 3 and 4. Now insert 3 again. Then move. 2 3s will anyway come together. Okay, good. So let's say we have there might have some cases where we have reached for the right array we have reached the end pointer, but with the left array we are at some way in the midway. There are few more elements. If you exit from the loop, these elements will be in the new array, but these elements will be missing. These elements are already in the sorted sequence. What can we do? Just take and copy them in the remaining part of the array. Can we do that? Okay, think for a minute. Ashutosh says yes. I'm basically discussing about the condition where all the elements in the right array have gone into the sorted array, but only few elements of left array went into the sorted array. There are few elements which are still left, but the while loop will get exited because R is exhausted with its elements. We already know our left array is sorted. As we know that left array is sorted, can we just take all these elements, copy them here? Okay, Ashutosh and Sachin says yes. Yes, ma'am. But we have to increment I and j. Yes, that's right. So let's say I write a code like this, while I less than L dot size. Then what to do? just keep incrementing. ARR of k is equal to ARR of k is equal to L of I. Increment both I and increment k also. This is the case when left array elements are left. Similarly, right array elements might also be left out. If that is happening, write a while loop for that also. J less than R dot size. Then do AR of k is equal to R of j, j plus plus, and k plus plus. Close. I'm closing the function also here. Okay. And once, let's say this is our first while loop, this is a second while loop, this is a third while loop. Definitely our while loop, when code exits from this while loop, either left array is completed or right array is completed. So either it will go into the second while loop or third while loop. It might not go in few cases, but most likely, I mean, only when simultaneously both of the sizes become 0, it will happen. But generally, it will go into, I mean, I'm not going into deep of that because if you dry run, you'll understand. So first loop will get exited when you have exhausted right array or left array. So either you will go into the second loop or you will go into the third loop, but you will not go into both the loops. And now if we observe, we have the duplicate R and left and right arrays. But as we have replaced our original array itself, we have merged the two arrays. We have merged the two different sorted parts into one single sorted part, and we have replaced it in the original array. So it's like we have received 3, 10, 3, 5, and in the indices 4, 5, 6, we have replaced 3, 5, 10, and we have returned back to the merge sort. Return back to the merge sort function, which initially called us. Where is that function? Yes, merge is called in the merge sort function. I'm done with the merge part, go back to the merge sort and perform any other operations you have. Is the algorithm clear? Okay, Ravashankar says yes. Ashish says yes. Okay, Ankit also says yes. Sachin says yes. Manish also says yes. What about remaining people? Rashmeet, Ashutosh. Okay, Vishal says yes. Good. Rashmeet also says yes. Ashutosh is clear. Okay. So most of you are clear only, but just we'll do a very, very small dry run and we'll stop. Okay. What was our array? 161483. 161483. 161483. 10 and 5. Okay. 10, 5. Okay. So my first call was made to the merge sort. This particular array 0, 1, 2, 3, 4, 5, 6. So 0, 6. Then it has called two different functions. It has called merge sort of ARR 0, 3. Merge sort of ARR 4, 5. Okay, two functions are called. And this function again called two different functions. Merge sort merge sort of ARR 0 and 1. I'll be using MS for the merge sort. So merge sort of ARR 2, 3. Again, merge sort of ARR 4, 5 and merge sort of 6. Okay. This has broken down into merge sort of ARR 0, 0, merge sort 1, 1. This called merge sort 2, 2, merge sort 3, 3. This called 4, 4, 5, 5. This is already this merge sort here. Low is equal to high. Low is equal to high. It has simply returned. This function is returned. Here also, every other function doing nothing, these functions have returned. Okay. When a parent has called 2 of its merge sorts, 2 of them has returned, then merge function is called. This is the parent. Parent has called 2 merge sorts. After 2 merge sorts are called, then merge function is called. Then merge function will come into play. Okay. Then it has performed the merge operation on these 2 things, and 0 and the first position, it has set it right. The merge function will do the job. So this is done. After merge function is done, then execution of this sort is done. Similarly here, after these 2 merge sort are completed, this parent will call merge on its 2 children. And similarly here also, then it will call merge. After merge happens, this merge will happen. Once its 2 children merge sorts are completed, then this particular parent will call merge on its 2 children. Finally, it will return a sorted array. Those who have maybe slight doubts also, I think things got clarified now. If everything is clear, we'll take a 5 minutes break and then start with the next topic. Can I get few yeses and then take a break? Still any doubts? Okay. Before stopping, I have to discuss one more thing also. I did not discuss the complexity. So complexity is what something is very, very important to the merge sort. Okay. Because yes, okay, clear, good. See, in binary search, if you observe, you have these elements. You split it into half. There are only log n steps. Log n separations only will be there. Similarly here also, this depth is log n. Everyone agree to that. The depth of this tree will be the depth of this tree. The number of steps will be log n steps, not more than that one, because you're breaking at mid every time. Okay. So there will be log n steps. What is happening at each step? You're doing a merge operation. Merge operation, here it is happening on 2 elements. Here it is happening for 2 elements. Here it is happening for 2 elements. Here it is happening for 2 elements. Let's for suppose say that it also had 2 children. It is happening for maximum of 2. It will happen 2 steps. This will take 2 steps only. So merge operation is taking us O of n time only, right? If you have n elements, so it will take O of n time. So combinedly at each iteration, the maximum number of merges, individual merges, when you combine the number of operations for each merge at each level, maximum then can be O of n only. Here there'll be O of n. Here you are adding 2 elements. Here 2 elements. 1 comparison or 2 merges, or you'll do a 4 merge plus 3 merge. At each level, combined of all the merges, combined complexity of all the merge operations at each level will be n only. Do everyone agree with that one? Okay, Ashutosh says yes. Sachin also says yes. Rashmit also says yes. Okay, Manish says yes. So if you say merge sort of this one, these both are done. If you perform merge operation, 2 elements, 4. Here 1 element, here 2 elements, 1 element. So it will be 3 operations, 3 plus 4, 7. 7 elements are there. At each step, it will become 4 plus 3 or 2 plus 2 plus 2 plus 1. So at each step, you will have n merge operations, and maximum levels can be O of n. So the time complexity of the merge sort is n log n. Very important. Whatever the algorithms which we have discussed previously, all of them have a time complexity of O of n square. Because we are using this strategy of this particular strategy is called as divide and conquer. You divide, you set those things right, then go back. So a general hint is that whenever you want to reduce complexity from O of n to n log n, then you might have to think in terms of divide and conquer techniques. Divide and conquer kind of technique. Generally, all those things which have this log n complexity, either they involve this divide and conquer technology algorithm, or they involve binary search. Okay. If everything is clear, it's 3:35. Till 3:40, you can take break, or let's say 3:45. Take break till 3:45 and then come back. Okay. Yeah, okay. 3:45, break till 3:45 and then come back. Everyone back? Okay. Everyone back? I'll break this lecture into two parts so that this is a different concept. Space complexity will be often, yes. I mean, let's say if you the left and right subarrays, if you initialize them at the first one and make use and keep using them, like you can do what you can do is you can initialize left subarray to be of size and right right part to be array of size. Copy the elements, keep track of its size also. I mean, every time you use it, obviously. If you do mid minus low, you'll get size of left array. And if you do high minus mid, you'll get the size of the other array. You know the size of the array, you know till where elements are there. You can keep reusing the space only. But these things you have to define globally. Otherwise, what you can do is after pushing into the vector, you can pop back from the vector. Then the space complexity will be O of n. And one more important thing which we observe is this is a merge. These are recursion calls only. When you call merge, in left and right you assign some space. When this function is popped out, your operating system itself will release the space and make the space available for other variables. So that way also it will take O of n space. If you want to be more precise in the code itself, you can declare them globally. Rashmi, was that clear? Okay, right. Okay. So now the topic will be linked list. So first of all, why linked list? And we'll discuss about different operations we can perform. How do we insert, remove? So see, already we have arrays, we have vectors. Do we? Okay. Arrays has the property of fixed size and continuous memory. Vectors do not have the property of fixed size, but still the space allocated them is continuous, because just a quick recap of the vectors lecture, when we were discussing vectors, we are like default size will be 8 when you want to insert the ninth element. Then your operating system will search for a space of 16 and then it will copy the elements. Space of them is continuous itself. But suppose you're building very screen. Okay, sorry. Okay. So you have 8 and 16. Just a recap again. Arrays have fixed size and continuous sequences. Vectors do not have a fixed size, but still they search for continuous spaces to store their data. So suppose if a default size of vector will be 8, if you want to insert the ninth element, then your operating system your system will search for a space which can store 16 contiguous elements. Then it will copy those 8 elements and then insert the ninth element. But anyway, exponentially as the space is increasing, this copying operation will not take much time. We discussed about the amortized time complexity. If you remember, that will be O of 1 only. Okay. Now, suppose when we have huge data, when we want lot of space, and every time such contiguous spaces might not be available. Okay. Then there is a need for data structure. For a data structure which stores values in a non-contiguous space. Non-contiguous space. Okay. Say, suppose, yes, there is some kind of data structure which is storing the in random space. Suppose you have an integer only. You have 4, you have 5, you have 6. It is stored at the location 1000. It is stored at the location 5000. It is stored at the location 8000. We have elements, we have some addresses, but how do we traverse or how do we combine them as a single structure? In case of arrays, you know that they are fixed size, and if you do ARR +1, you go to the next address. The difference between these addresses is 4 only. So your access has become easier. But how do we access these things? And how do you maintain that sequential property? Okay, after this data, I have entered this data. After this data, I have entered this data. Some sequential order also have to keep track of them, right? So what it will say is, so let's slightly modify this data structure and say, this is the first element which you have inserted. Along with this element, also store the address of the next element, so that this element can point to this element, and store the address of the next element so that this can point to this one. When you have no more elements in the set, then point this to null. Okay. To define this data structure, a simple integer and all those things won't be sufficient. In case of C++, in case of C, you might have heard about structs, which are basically custom data types. Okay. Let's call this a node. Okay. Maybe it has 2 elements. First, what it has is a data. Next, what it has a you're storing the address of another node. When you're storing addresses, you need pointers. Okay, what I'm saying, of type node, pointer, a pointer which can store the address of a node and name it the next. Okay. We are using a node star because this is a node. This is also a node. You want to store the address of another node. Then you have to use a pointer of type node to store the address value. Okay. Got it? Any doubts still here? $5,000 is working as a pointer. So this is basically the address. Address won't be like this, but just for understanding, I have written them to be like this. For storing address value, repeat node star next. Okay. Say suppose in C, we have data types like integer, character, or float, or double. But for suppose, let's say you want to store the coordinates. Okay. So there is a data type called as struct, which can be defined such that you can store data in one data type, and you have to name that data type. So your data type now will be node. Okay, and then you can compactly store all the things related to one particular entity. Okay, you can say int data and int data 2. Okay. This is in general what a struct looks like. Okay. But what kind of struct do we need for linked list is that we want one part of it to store a data of integer type. And the second part of it, we want it to store the address of next node. Okay. So what are pointers? Pointers are basically the variables which store addresses. Okay. Basically, in a pointer, you will have some addresses stored. This address will map to some particular space in your system. But what do you store in the space? In a space, you can store an integer, you can store a character, you can store anything. Okay. So for a pointer to mention what kind of data is located at the star, we typecast that one and declare things like int star a, which means that a is a pointer variable and the address in a contains an integer. That's what this notation means. Okay. Now, if we do node star next, which means that I'm having a pointer of variable next. The address which the next contains actually is a node which has a data. So it has particular data structure. Ravi Shankar, is it clear now? Okay, great. So, okay, now let's see. In your program, if you say you have declared a space, say you have declared a vector or you have declared an array, you will say array of size n. You will mention the size. Vector will take the default size. Even before you start running the program, your program is given the space. Okay. But whereas when it comes to linked lists and all these things, the space is assigned during runtime. Okay. When the space is assigned during runtime, you have to keep requesting your system for space. Based on the requirement, you'll keep asking your system for some space. Okay. System for space based on requirement. Okay. How do we do that? Let's see how we'll do it in C first. In C, there is a function called as malloc. It takes input of how much space you want and outputs a pointer, a general pointer. Okay. If you want to store an integer in that space, what you basically do is int star a, typecast this general pointer to an integer pointer to malloc and say, I want space which is equal to the size of integer. What basically happening is here is malloc function requests operating system for some space. How much space you have to mention here. It will give that much of space. Okay, it has found that much of space. This space will have an address. This malloc will return an address. But this is a general pointer. But to make sure you assign that to an integer pointer and say that you're assigning an integer, you'll be storing an integer here, you have to typecast that one into an integer pointer. Because A is defined to be an integer pointer. If you don't assign an integer pointer, you'll get an error. You can't assign a general pointer to an integer pointer. So you have to typecast and then only assign. Is malloc clear? Or do you have any doubts on malloc? Am I audible? Ma'am, please repeat. Okay. What about remaining? Do you want me to repeat? Okay, let me repeat. So, in case of vectors and arrays, there is some fixed space associated with that one. So, whenever you write an algorithm, when you compile itself, that much of space will be allocated to this program. Okay, this program will use this much of space. Default, if it's a vector, default, let's assign 8 space first of all. But when it comes to linked list, they are dynamic in nature. Okay, and based on requirement, they'll be asking space from the operating system. That's the main use of linked lists. So based on requirement, based on the user input, your program will keep asking space from the system. How will it ask space from the system? Using a malloc function. Okay, malloc can communicate with the operating system, whereas your general programs cannot. It's a specialty of that malloc function. Okay, malloc function, every function has some input and output. The input to the malloc function should be how much space you want, so that it can require that amount of space from the operating system. You have to pass how much space you want. After you pass space, what it will do, it will ask the operating system key, okay, I want this much of space, give me that much of space. It will give that space and it will return a pointer to that address. Okay, pointer is basically the address. It will give the address of that space. Okay, it will give you the address. But as we have already discussed, int star a means, okay, address. What are you storing in that address? You are storing an integer. So it's called as an integer pointer. This particular address is pointing to an integer value. Similarly, malloc has written me a general pointer. If I want to turn that, if I want to store an integer in that particular value, I'll typecast that one into an integer pointer. General pointer, I'm converting that to an integer pointer. Are the things clear? Okay. What Ashish also says yes. What about remaining people? Okay. This is what generally happens in C. But whereas in C++, you have a keyword called as new. Okay, what does this new do is, this new internally performs this malloc. Okay, you need not mention space and all those things. You say, I want a new node. If you say, I want a new node, we have defined node above it. What it will do is, it will return a pointer of type node and assign that one to it will do all this operation. It will do malloc, it will assign size, it will do a typecasting, it will do everything and return the pointer value. You can do node star, let's say some temporary pointer is equal to new node. Simply call that one. You will get a pointer which is pointing to a node type with data and then address to the next pointer, or maybe null. Clear? As a homework, explore the keyword new. Okay. Now, we have discussed about all these things. So, for a linked list, important points are that it's dynamic. Okay, dynamic. So space gets allocated based on need. Vectors are also dynamic. Based on requirement only, the space is increasing. Linked list is also dynamic. Apart from being a dynamic, it's also non-contiguous. Okay. identifier okay. See, suppose you have an array. Array has some address. If you do ARR of 0, ARR of 1, you'll be able to access the remaining pointers. For vector, you have a function v.begin, which returns an address to the first pointer. Then you can also do v of 0, v of 1 to access the further elements. But how will you access all the elements? How to access all the elements from the linked list? So what do you think is the most important element in the linked list? You have an element which is pointed to the next element, which is pointed to the next element, which is pointed. The last element is pointed maybe to null. Yeah, there's no elements further. Address, okay. Yes. This variable has some address. This also is stored some in address. This is also stored in address. This is also stored in address. I'll try to ask the question in a different way. What is one particular address? If you have that address, you'll be able to access all the remaining elements. Let's say this is address 1, 2, 3, and 4. If you, let's say you're given an option to choose one address. Given that one address, you should be able to retrieve all the remaining elements. Last one, address 4, okay. Start, okay. Okay, any other answers? Okay. Start and address 4. Okay, let's see. Suppose, say I have address 4. What address 4 contains? It will have some data and it has null. Okay. Just given this node, I'll be able to access only these two things, nothing other than that. Can I go back? Because this variable at address 3 has data and address 4 also. But address 4 does not have that. Okay. And similarly, this is address 2. Address 2 has address 3 stored and it has its own data also. And address 1. Okay. It has data, address 2 stored. If I'm at address 4, then I'll be only able to get its data. But if I have address 1, I can get address 2. I can go to address 2. Then I can access address 3. I can go to address 3, get data, access address 4. Then I can go to, then I can get address 4. I can get its data. Then I'll see, okay, null. There are no more elements. I can stop here. So once you have this first data from a linked list, you'll be able to access all the remaining elements. Yes. So this is also called as head pointer. Yes, from address 1, we can access all. Okay, done. So again, just recollecting the important points for a linked list. It's dynamic. Sorry. It's dynamic. It's non-contiguous. The main important thing it should have is a head pointer. A linked list is characterized by its head pointer. Okay. And then, and linked list is unidirectional. Okay. You can access elements from here to here. Or if you start with address 2, you can go to address 4. But if you start at address 3, there is no coming back. Only you can access the elements in one direction. Okay. This will come into use, a lot of use in the problems to decipher and come to a solution. So keep this point in mind. When coming to problems, the head pointer and the property of unidirectionality will come into a lot of use. Okay. So let's say we have defined a struct. Those who are using C still, generally for struct kind of variables, we also define constructors. So let's say, suppose we have int data, we have node star pointer next. Okay. And then you can also define a function which says capital N node, take input as X, return a node such that its data is equal to X and next is equal to null. You put that value X and return that one. Okay. So when you define a node, if you also pass a value, assign that value to the X. This is, in other words, called as a constructor. And this is in general for everything. But if you go to another platforms like LeetCode and all these things, all these structure, whether it's C++ or C, they'll define all these things. They'll define data, they'll define all these names. They'll also give you these initial constructors, which you can just make use of in your code. Okay. But this is the basic structure code. Even if you want to do it in C++, then use the keyword new. Okay. Ma'am, if we access through one element in remaining, then why is it not contiguous? Yes. So it is not contiguous in the set of address space. So in case of an array, the address of this element, suppose if this is 100, this is definitely 104. If it's 4, because integer takes 4 bytes of space. Next array is definitely 108. Next address is definitely 112. But this is not the case with linked list. Sachin, did you get my point? Okay. So now we will see. We have we know how linked list is functioning and all those things. Let's construct the linked list. How do you insert elements into a linked list? Okay. You're given n elements. Insert them into a linked list. Okay. The first element which you are inserting, see, there are two ways in which you can form the linked list. You can take the first element here, then you can keep the last element at the first, or this can be the first element, or other way of storing element is this can be the first one and first element first, last element last. Okay, there are two ways in which you can store. Okay, I'll give you 2 or 3 minutes. Think how you can store these things. Okay. If asked to write a code to insert n elements, into an array? How will you do that? Take the position empty, then store. Ashutosh, can you elaborate a little bit? And one more important property of our linked list is that based on the requirement, we keep asking for space. I'm saying insert n elements, but as you insert element by element, you keep requesting space. That's one hint. And then think about it more. You need to have a head pointer. For convenience, sometimes you can store the tail pointer also. Suppose this is your head pointer and the last pointer is called as tail. At node, yes. Okay, yet you will be inserting at the nodes. Let's say we'll not use this procedure for now. Let's follow this convention. The first element which you have insert has to be at the head pointer. The last element which you have insert has to be at the tail pointer. This is the code which is expected by you to write. Okay. Okay. Suppose, say that, do you want me to give a solution or will you think for a little bit more time? Okay, let me write the code. Okay, see, I want to keep track of head pointer. I want to keep track of tail pointer. Tail pointer because so that my insertion will become easy. Once I know the last pointer, I can create a new node, attach it to this one and change my tail node to this one. Move my tail pointer here. I need the head node because generally for any linked list, head pointer is very important for me to iterate towards all the elements. So it's not about just creation. Afterwards, I should be able to access it also. Right. So I need head pointer and tail pointer. I need two pointers. Let's say node star, my head pointer. Initially, I'm saying null. I'm not storing any address. It's an empty space. Okay. It's my head pointer. It does not have any address. It's just a null pointer. It does not store anything. It's just a null. Okay. Then I have node star tail. Initially make this one also null. It has nothing, no address, nothing. Okay. Remember, only when you do malloc or when you do new, you will get some space and address. Till then, these are just the variable names. They don't have any space. They don't have any address. Okay. Remember that one. Let me use one temporary variable also. Okay. Let's say I did temporary variable, and to this temporary variable, I said new node. I'm using C++ conventions only. Node is the name of my struct. Okay. I did new node. This temporary variable now has some address. It stores some address. It has some address. Okay. This has been assigned some pointer value. Now it has some address. Let's say 100 or something. Okay. It has been allocated some space. Okay. Now it does not store any data. Generally, it does not store any data, and it pointers to a null pointer, but it has this particular variable have been given some space. It has some address associated with that one. Okay. And these two does not have anything. They don't have any address associated with them. Let's say while n minus minus. Okay. Suppose take input of the element. Okay. Let's say n in the temporary variable which we have stored, temporary variable of data is equal to x. Store this one in this data. Use a temporary variable for our convenience. Okay. Now let's say, see, if my head pointer is equal to null, so one element also has not been inserted till now, then what we'll do is, it's a pointer variable, but it does not store anything. Okay. Now what I'll say is, simply I'll say, now make this temporary value, this temporary address, this 100, because I've already stored my x date also. Make this one head. Give it that address. Whatever the temp address is there, give the same address to head. And initially, when there is a single element, my tail is also the same. So make my tail also temp. And remember, all the three, head, tail, and temp, they are pointers. They store addresses. That's it. So basically, this tail will store 100. Now I said head will also store 100, tail will also. At tail is at location 100. Now this is at location 100. At location 100, what did I do? I said temp of data is equal to x. And initially, the next pointer, by default, it's null. This is how the structure is looking till now. We have inserted one element. Is that clear? Till now, do anyone has any doubts? Sachin says yes. Okay. Okay. What about remaining people? Any confusions? Okay. Cool. Now, if this is not the first element, what shall we do? I know a tail. New element, I want to insert it after tail. What I did temporary, now I have stored data also. Okay. What I'll do is, temporary, I have stored the data. Okay. What I'll do is, tail of next is equal to, now create a temporary variable, create a new temporary variable. This temporary variable is over. Now I'm saying I want a new temporary variable. Create a new temporary variable. Okay. Every time create a new temporary variable, because every time you want an address, right? So create a new node, fill x value in that one. Okay, every time create a new node, because every time you want to insert a space, you want a new address space. So every time you have to create and make tail of next is equal to temp. Now I have tail. What did I do? My head is also at the same place. Now initially say my x is equal to temp. Now I am saying tail of next is equal to temp. Whenever you give new, a new space has been given, it has some address. Store this address here. I'm saying tail of next is equal to temp. Now, after inserting this next element, now this should be my tail. My initial tail was here. Now I'll do tail is equal to tail of next, which means I'm moving my tail from here to here. That's it. close. Okay. Is it clear? Or any more doubts? Or do you have any doubts? If you have any doubts, you can ask. I'll wait for a good amount of time because you need to understand what is happening. What are we doing? When is new address provided? When is new space given? How are we changing the addresses? All these things is very, very important. So take your time to understand. If you have any doubts, ask. If you don't have any doubts, type yes so that I'll understand how many people actually understood this one. Sachin says else part. Okay. Repeat while part entirely. Okay. Okay. So let me repeat in general. I'll repeat. Then let's see how many people will understand the things. Okay. C in X and temperature temp node star is equal to new node. Okay. So let's assume our values are coming as 10, 20, 30, so on. Okay. Now let's start with the first one. Let's say input is X. I said create a new temporary variable. Create a new temp. Temp is of type node star, which means that temp will store an address. Will store an address which points to pointer. New pointer is basically our malloc function, which requests space and it will return the space. Let's say initially temp stores an address of 1000. Okay. Temp stores an address of 1000. So basically there is one block whose address is 1000. I'm saying to the address which temp is pointing to, temp of data, make it X. So in this part, store 100. So here I'll write it here. This has address 100. Okay. Hence, sorry, say 1000. It is storing 10. By default, let's say our next pointer is initialized to null. We have done that one also. By default, it is null. Let's assume that it's default null. By default, it will be assigned null only. That's done. It has been. Now, this is my temp. Okay, this is my temp. Temp is storing 1000 address. Let me not, this is not. My temp is storing 1000. This is just like a integer only. But here it will store the address of some data type. That's the only difference. Okay, my temp is 1000. This is some space on my computer which has address 1000. The data stored in it is 10, and the next pointer stored in it is null. Okay. Next, what condition did I check? If my head pointer is equal to null. Yes, initially I initialized my head pointer to null. I have not stored any address in that one. I just marked it as null. Now what I'm saying, if head is equal to null, this is the first element which I'm inserting. If that is a first element which I'm inserting, I want to mark that one as head pointer so that my access to the linked list will become easy for me later. So what I said, head is equal to temp. When I say head is equal to temp, I'm making head also store 1000. Okay. And when there is a single element present, my tail is this one, my head is also this one. And what I said, my tail is also 2000. This has what has happened in the first iteration. Now, my linked list has a head pointer, it has a tail pointer. Both of them are pointing to this one. First iteration is clear for everyone? sorry, tail is also storing 1000. Okay. Can I get a little bit more number of yes? Then I'll proceed to the next step. What happened to Ashutosh and all remaining people? Okay, cool. Now, let's say second step, our second iteration. Second iteration, the input value is 20. Then what did I say? Temp, new node. Whenever I say new node, new space will be allocated. Now, let's say this temp is given the address 2000 because 1000 is already occupied. It has searched and it has given the address to be 2000. Okay, temp is equal to null. It's not null because my head is 1000. Head is not equal to null. So it will not go into this loop. What did I say? Else. Okay. Else, what did I say? Tail of next is equal to temp. Okay. What is the address my tail contains? My tail contains 1000. What I'm saying? Okay. Tail, go to 1000 and go to its next. This is the data part. This is the next part. Go to data, go to next and store temp value. What is there in temp? 2000. Now store here 2000. Here store 2000. But what did I previously do? I got a new space of 2000. In that I kept data is equal to x. What was my x now? My x is 20. And this is a null pointer. My tail is here. What did I do? Tail of next is equal to 2000. 2000 address has this one. What does my head pointer and tail pointer do? Tail pointer points to the first element. Tail points to the last element. Now, when I insert a new element, my tail pointer, I have to move my tail pointer from here to here. Basically, in my tail, I have to now store 2000. But where is the 2000 address? In my tail of next. This is my initial tail. Okay. My initial tail is 1000. I want to change its address to 2000 because this is my last element now. What did I do? Tail of next. Tail of next is equal to, okay, tail of next is equal to temp. Oh, this step is already completed. We completed that part. What I'm doing is tail is equal to tail of next. This is my initial tail. What does my tail of next contain? It contains 2000. So I'm making my tail is equal to 2000. If my tail is 2000, I'm moving it to from here, I'm moving it to here. And now my head pointer has 0, it has next, it has 2000. So this and this one are connected. This particular node can point to this node now. How is my final linked list looking? I have 10, 2000. These both are stored at the address 1000. And then at the address 2000, I have 20 and it is pointing to null pointer, 2 pointer, which means it is pointing here. I have my head pointer here. I have my tail pointer here. At the end of second iteration, my head is 1000. My tail is 2000. Yes. Are the things clear now? And similarly, I'll repeat the same process for the elements to come. Basically, after from now onwards, I'll always hit the else condition. I'll not hit the if condition. Okay. Why we took n minus minus? Okay. So basically, say suppose I want to insert 3 elements. From after I insert element, I'll do 2 and 1 and 0 will come. So while basically, what does while evaluate to? While if it's true, the loop will execute. If it's not true, it'll exit. So anything other than 0 is true. So when it hits 0, it will exit from the loop. That's it. N is nothing but the number of inputs which are trying to give. That's it. Any doubts? Anything other than 0 is true. Only 0 is false. Okay. Maybe take 2 more minutes to digest this one. We'll go to the next part. Very, very important how this address is changing. So, I mean, generally what happens is at the very first sight, we're thinking, okay, pointer is storing some address and all these things. But visualize that address as a number. Your address is also a number. Actually, it's a number. It's a 32-bit address. It's a 32-bit number. Okay, or 64-bit number. It will depend on the system though. So think of it as a number. Things will become very simpler for you to understand. And if you want extra space, you have to do malloc. Only then you'll get an extra space. Till then, you'll not get the extra space. Storing in this one will be stored in this one also. So don't think pointers are some alien creatures. They are normal things only. Imagine them to be simple integers. You'll be able to decipher things better. Ma'am, we can reduce address. How do you want to reduce the address? I mean, yes, I said think of it as an integer. That is just for your imagination purpose, not in terms of operations. All operations which can be performed on integers cannot be performed on addresses. That statement is just for your visualization. That's it. Don't get confused. You can't do head plus plus and it will become 1001. No, that's not happening. Okay. Okay. Everyone clear? Do anybody has any more doubts? No. Okay. How do you traverse? I already have given hints on how to traverse the linked list. So can somebody help me with the code? How to traverse the linked list? Where do we start? Suppose I have a linked list, 2, 3. When I write a linked list, I might avoid writing the address and all these things, but default assume that addresses are stored. Okay, let's say 10, 6, and this is pointing to null. How do I traverse this one? I have my head pointer here. Head node, yes, 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 done. Good. Okay. Let's say I print every time. I print C out head of data. Okay, end line. And then after printing this one, I want to go to the next value. What did we do when we want our tail to move? We did head is equal to tail is equal to tail of next. Here, can I do head is equal to head of next? Yes or no? Think about these 2 lines, what I was trying to write. I'll say while it is equal to null, iterate. This is the simple code for traverse. Try to do a dry run and let me know. Otherwise, I'll do a dry run. Traversal code. Okay. Okay. I think these are the functionalities of stack, not linked list. And I think it is, yeah, I think pushing popping into the stack. Yes, yes. These are the codes for stack. Yes, ma'am. Stack using. Yes, yes. I said now, how do you traverse a linked list? Stack is a whole different new data structure. Stacks can be realized using, stacks are a separate thing when it comes to C++. And if you want to realize it using writing in a C, you can write it using an array also. Linked lists are a separate structures. Stacks and all these things are contiguous spaces. Only this linked list gives us the advantage of the dynamic being it and dynamic, and it's both non-contiguous also. So I was asking about how do you traverse a linked list, not a stack? Node next. Okay. Yes, yes, right. Wait. While PTR is not equal to null. Okay, actually I made a mistake. We have to iterate till it's not equal to null, not when it's equal. Till it's not equal to null, we have to iterate. Not equal to null, print the element, then do pointer is equal to pointer of next. Yes, it's right. Yes, right. Ma'am, I have both the codes. Acha, okay. So meanwhile, did remaining people try to think what's happening? Okay. Let me do a quick dry run. Let's say this suppose is 100, this is 200, this is 300, and this is 400. Okay, I start initially my head pointer will have an address of 100. Okay, this is my first iteration. Head is not equal to null. Yes, head has a value 100. It's not equal to null, so it will go into the loop. And I said print head of data. Head is 100, which means it's storing an address 100. When I say head of data, it will go to the address and it will get the value which is present in data. So it will print 2. And now I said head is equal to head of next. My head is initially 100. 100, what is stored in next of it? 200. Basically here it is stored 200. So I'm saying head is equal to head of next. So head is becoming 200 at the end. Okay, after first iteration. Second iteration, my head is equal to 2000. It's still not equal to null. Then okay. Then print data. What is there at 200? 3 is there. So it will output 3. Then head is equal to head of next. 200 internally will have an address 300. Head 200 of next will have 300. So I'm saying when I do head is equal to head of next, basically I'm assigning a value 300 to the head. Okay. Then third iteration, 300 is not equal to null. It will repeat. The value which is present at 300 is 10. It will output 10. Then we do head is equal to head of next. 300 next has a value. It has an address. It has 400 address stored. Then it's still not equal to null. We iterate again and we print 6. After printing 6, 400 has the 400 of next is null. Okay. Now head is equal to null. And then we exit the loop. Is dry run clear for everybody? So from here, you have been moving here, you have moved here, you have moved here. Finally, we reached null and we stopped. Okay. Okay, great. One disadvantage of this approach is that head pointer is the initial pointer. We have moved it, and finally it became null when you're out of the loop. Now, if you want to go back and check the linked list, you don't have anything to search, right? So often, head pointer is not used for traversal. What we do is basically create a temporary node, temporary pointer, and first get your head value in the, store your head value in some temporary node, use temp to transfer while temp not equal to null, see out temp of data, end line, and then do temp is equal to temp of next. In that way, after this loop, temp will become null, but your head will still store the address 100. So if you want to make any operations after the traversal is done also, you can do it. Did you get that point? This is very, very important. Often what happens is you'll write the code, you'll transfer, you'll search for the head pointer, head pointer will now be null, you will not be able to access it back. So this is very important. Understood what I was trying to say? Okay. So basically I'm saying is, you want to manipulate certain value, but that you want to keep track of that value also. Basically, suppose say, in case of integers, I said y is equal to x. I made manipulations around x. Now x value is changed. Now, if I want to go back to the value, I can't go back. So before changing itself, I make a note of it in y so that I can use it later. That's what I have done here. That's it. Nothing new there. Am I audible? Okay. Did you understand why we are using some other temporary address variable to store the head and then traverse? Okay. Shall we discuss just one more problem and then stop? Just a very, very small one. Or, okay, let's stop for today, I think. We'll stop for today. We'll discuss later. Okay. We'll stop for today. Enough. We'll discuss tomorrow. Okay. Cool. So did everybody understand what we are trying to do till here? Can you send the code for 4 divisor? I've been asking from a long time, but I also forgot. I'll have to check. A 4 divisor problem of dashboard, or which question? I mean, can you, there are many 4 divisor questions, so that's where I'm getting confused, or which I have given. Achha, okay, then I'll check. Fine, I'll check. Okay. I thought you were trying to solve some new problem. Okay. Cool. Any more doubts, or did you have a good understanding of what is happening in linked list? If not, I'll take 5 more minutes and explain. That's the reason I'm asking repeatedly. See, you know what is the advantage of linked list? Any problem, say suppose arrays or arrays, trees and all those things, there are many algorithms. Given a problem, you will have to choose between many algorithms. And whereas linked list is not like that. The algorithms on linked list are, ma'am, can you name all the topics covered today? Sure, Lalit, I'll do that. Hi, Lalit, I've not seen you messaging today. Do you understand what we are trying to cover? Okay. So, linguists, there are very, very few algorithms. Get them right, understand this address manipulation. You'll be given an linked list question. There is no question that you'll not get the idea of the question. Within 1 minute, you'll get an idea. Linked list is about implementation. So it's like a major, major advantage. If you know how to manipulate these write 1-2 programs on your own, print addresses and check how addresses are changing and stuff. Okay, let me show you a small code. Okay. Okay, can you? Yes, ma'am, I was quite busy. I'll read it later. Achha. Okay. Cool. Anyway, this particular lecture notes will also be available in the folder which I've shared with you. If you want to revise through that also, you can. Okay. So this is basic. This is a simple code for linked list. So basically, just insert and display function. Nothing other than that. But what I did is, whenever I insert, I checked, what is the initial head address? What is the temp address? How the head address have changed? Okay. How temp has changed, how head has changed. And while displaying also, I was printing all the address. What is there in temp? What is there in temp data? What is there in temp next? So are the addresses changing correctly? So I have do a dry run and use these printfs, use this cout statements also to check what is happening with the code. Okay, I'll not send this code today. Experiment. With handwritten code I have written, try to code that up, try to put these printf statements and observe how things are changing with linked list. And trust me, if you understand the insert code, if you understand the traversal code, every question of linked list you'll be able to do. Any other topic with this much of confidence I can't say, but if you know how to manipulate your pointers, if you understand what your pointers are exactly doing, you'll be able to solve any linked list question, whether it be a hard level or any level question, you'll be able to do. Okay. So just to summarize. Okay, we have discussed about insertion sort. Okay, and we have discussed about merge sort. As a homework, implement both the things. Almost the codes are there in the notes. Okay, and then we have we discussed about linked list theory. We have discussed about the insert function and traversal function. Okay. Both insert and traversal are there. Implement this part also. And apart from this, there are few problems which are attached in, say, searching and sorting section. In the doc itself, which is there in the group description. Searching and sorted, check in group description, and try to solve all the problems. But the very important problem you have to solve is, there is a problem called as count inversions. Okay. This is basically the extension of merge sort. Okay. It's a merge sort extension. Try to code that up. Okay. So let's say you have 1, 2, 3, 4, 5 problems to solve. Remaining, I leave it to your own, own time, based on time and your quality, solve the remaining things. Okay, then if you have any doubts, you can ask. Otherwise, we'll call it for the day. Could you see my screen? Not visible. Okay, what happened? Let me check. You can see it now, right? Okay. Okay. So insertion sort, merge sort, linked list, both insert function and traversal function, searching and sorting, count inversions problem. Okay. Okay. If you have any doubts, you can stay. Otherwise, feel free to leave. I'll stay for maybe another 5 or 6 minutes. Looks like we have to take little extra classes to complete, because maybe we might require 1 or 2 extra classes to complete the things. I'll let you know. Probably let us think if we can complete, we'll complete within the class duration, because you have other things to do also. If not, we might need some few extra lectures. But this Saturday and Sunday, let's take off. Oh, you have Saturday and Sunday. Okay. Then you can practice many things. Okay, let me get back to you on the group if you have. But as of now, complete these things. I'll message on the group if you have to solve any extra problems and stuff. "48 people are still there. Okay. Looks like there are no doubts. Then I'll also close the meeting. Okay then. Bye.